Hello, welcome to a talk that I've decided to call Climbing Math and the American Death Triangle. My name's Daniel Vickers, and I am a physicist. I work for the Georgia Institute of Technology currently, and I'm also an amateur climber, and I've been working on getting some certifications for climbing safety. And in one of the classes I've been taking, we came across this concept of the American Death Triangle. I couldn't find any math online talking about the physics behind the American Death Triangle and exactly what's going on. But I think that there's very interesting information there. And I think that if you're capable of following the math with me, then it will give you a lot of information to better understand how forces in climbing work in general and how to better mitigate some of this risk. So that's what I want to talk about today. Again, as I said, there will be a little math. I'm keeping it all strictly at a high school level, but there will be some, and hopefully you'll be able to follow along with me. So with that being said, let's go ahead and get started. And the first thing I'm going to talk about is what is the American Death Triangle. So it is this anchor setup shown in the image. I've taken this image from the American Alpine Institute. And in this image, you can see there's several things wrong with it. Obviously, the two carabiners at the top are not locking. The carabiner at the bottom, which is where the rope is going through, there's not a second carabiner that's opposite and opposed. And the sling is not redundant. So if the sling broke, the climber would fall. The rope would go down. But the problem that I'm talking about, which is the problem with all American Death Triangles, is the fact that the carabiners wind up forming this wide angle between them. And to give you a better idea, there's this other image that I've taken from the Wikipedia page about the American Death Triangle, where if you have this sling in red that is attaching to the carabiners, and then you have the weight at the very bottom, that would represent the downward force that is being caused by the weight of the climber plus the weight of the rope. It turns out that the carabiners wind up being in the direction of those blue arrows, and that is the direction of the tension on the carabiner itself. So the tension forces on the carabiners are in that direction. So that winds up meaning that if the carabiners have a non-zero angle, where they're not straight up and down, it turns out that there's a lateral force or horizontal force, and that horizontal force adds extra weight to each carabiner that it's holding. So hypothetically, if the carabiners were right next to each other, and so they were pointed straight downwards, both of them, each of them would be responsible for supporting half the weight of the climber. So about 50%, which makes sense to us. But it turns out that as this angle gets wider, the forces involved get higher. So, for example, in the image on the left, it looks like the carabiners are about 90 degrees apart. And if you go at 90 degrees, it turns out that the force on each carabiner is not half the weight of the climber. It is actually 0.71 times the weight of the climber. So 70% of its weight, not 50% of it. And things only get more ridiculous as you get to wider angles. The forces involved increase exponentially towards an asymptote of 180 degrees, where the forces are theoretically infinite. But at some kind of ridiculous value, so let's say the carabiners were at 170 degrees, it turns out that the forces on the carabiner are actually 570% the weight of the climber. So let's put that in perspective for you. The weight of a climber could be, let's say, 80 kilograms. And I'm going to assume like the weight of a rope is about 20 kilograms. So that means that the total force on the system would be about 1 kilonewton. Kilonewton is the unit that is standardized in climbing for measuring the strength of our gear. So that seems like a good unit to use. So 1 kilonewton is being exerted on the anchor point at the bottom. Now, let's say the carabiners are, as they are in the image on the left, 90 degrees. That means that each carabiner is actually supporting 700 kilonewtons. But if you used a different top anchor setup, you could make that go down to 500 kilonewtons. All right. So you can see that you could reduce the forces by a good deal just by changing the anchor setup that you have. In the extreme case of 170 degrees, it turns out that each carabiner is supporting 5.7 kilonewtons, which is a very large force. To put it in perspective, a very hard whipper that you would get from a sport climbing fall, those tend to cap out somewhere around 3.5 kilonewtons. So the forces on it just as a top rope, as someone resting on the rope, not moving, would be higher than someone falling, let's say 30 feet on a sport climbing fall. That is insane. And that just goes to show how important understanding how to build these anchors strong and redundant are. I will say, before I get into some of the math, a lot of people online like to say that this is fine because of the rating of the gear, that the gear is rated. For example, the nylon runner is rated to be about 20 kilonewtons, and the carabiners tend to be about 24 kilonewtons. And so everyone likes to say that hypothetically, this force is fine and safe to climb on. I am not certified and cannot say for sure, but this is officially not recommended by the American Alpine Institute. And I can just say that everyone should be able to agree that keeping the forces on your gear and everything involved as low as possible is the safest way to climb. And everyone should be interested in climbing safely. So that's why I think this is important. With that being said, I'm going to transition to the math portion of the talk. So just as a review, this problem is caused by having wide angles on the carabiners. And there's problems of this not being redundant, but mostly because of this high lateral force. And I'm about to show you how this lateral force comes out of this setup. And you can see this angle here on the right. So I'm going to draw my own version of the diagram in the previous page just to be able to add my own forces on it. So let's say hypothetically that you have these carabiners being at the two X's on top, and the anchor point is the one at the bottom. So the weight of the climber plus the rope is this downward force F that you can see on screen. So what are the forces that are on the carabiner? How do you get these values that are specifically 570%, stuff like that? Well, first of all, you need to figure out what is the tension force. So the tension force is along these red arrows that I've drawn. You can see the angle between them is this value theta. And I want to figure out what is the tension force. First of all, I know what the vertical force is. Newton's laws of motion dictate that the vertical components of the forces must cancel out in this system. So all the downward force that is caused by the climber and the rope's weight must be counteracted by the carabiners themselves by pulling up on that rope and on the and therefore on the climber. So it's very obvious that if the system is weighted equally, then each carabiner should support half the weight of the climber. So in this system that I've drawn it where it's symmetric, note that each carabiner vertically will be supporting half of the total force F. So F sub y, which is what I'm calling the vertical component, is F over 2. And then there's also this lateral component. And this lateral component we know is not 0 because theta is not 0. Okay? And that I'm going to call F sub x, the horizontal or lateral force. And we don't know what that is right now. I will derive it for you in a second. But I also want to talk about the total tension force. So we can get the total tension force by noting that F sub x and F sub y help form a right triangle, with F sub t being the hypotenuse. If you recall from high school, the equation, the Pythagorean theorem, helps you find the length of a hypotenuse given the side lengths a and b, where a squared plus b squared is c squared. In this case, I'm using f sub x squared plus f sub y squared is f sub t squared. So if I can find f sub x, and I already know f sub y, I can find f sub t. All right, so just a review before we finally start doing the equations. I know the forces are balanced. The vertical component is already known. It is f over 2. And this angle means that there is some value f sub x that's not 0. And we're going to use the Pythagorean theorem eventually to find the tension. So as a note, because I already said that the system's symmetric, and given a symmetric anchor, all the forces I calculate on the right are going to be the same as the forces calculated on the left. So I'm allowed to, by symmetry, just assume that I only need to figure out the stuff on the right, and that's going to make it simpler for us. So that's what I'm going to do. And I also wanted to find these angles. So the angle from vertical winds up being half of the angle between the carabiners, theta over 2. And to help it be easier for you guys to follow, I'm going to define phi. And phi is equal to 90 minus theta over 2, because phi plus theta over 2 is 90. It is a right angle in 90 degrees. So that's what I'm defining phi as. And now I want to get into actually solving f sub x. And I'm going to do that by using the trig functions, sine, cosine, and tangent to be specific. So in this example here, you may remember the mnemonic SOHCAHTOA, which is the mnemonic you use to remember how you relate which trig function in the angle to which sides of the triangle. In this case, I have f sub y. It's the only side I know. I have phi, because I will have the angle, and I want f sub x, this lateral force. So the thing that's going to relate it is tangent, where tangent relates the opposite in the adjacent sides. You can tell in the image on the very top right triangle. So based on that equation alone, I immediately know that the tangent of phi is equal to f sub y divided by f sub x. Okay, and now I can just solve for f sub x. So I'm going to multiply by f sub x on both sides, and I'm going to divide by tangent of phi. And I already know what f sub y is, so let me go ahead and plug that in. So I know that f sub x is equal to f over 2 divided by tangent of phi. Keep in mind, again, phi is 90 minus theta over 2. All right, so I have f sub x, and I want to get this back into theta now because I'm now going to go back to solving it in terms of theta. So I'm going to note that there's this interesting trig relation. 1 over tan of phi is equal to tan of 90 minus phi. But 90 minus phi is theta over 2. So 1 over tan of phi is equal to tan of theta over 2. And so I can note that dividing by tan of phi is the same thing as multiplying by tan of theta over 2. And so now f of x is equal to f over 2 times tangent of theta over 2. All right, time to solve for this component for the total tension on the carabiner. So f sub t squared equals f sub x squared plus f sub y squared. I already know f sub y, and then I also just solved f sub x, so I'm going to plug it in. To make things immediately easier, I'm going to take out this f over 2 squared term. So I know that f sub t squared is f over 2 squared times tangent of theta over 2 squared plus 1. And yeah, this may seem to be a little complicated. I'm going to use a trig identity to simplify this a little. So here's a list of some basic trig identities. What I want you to notice is this one here. 1 plus tangent squared of x is secant squared of x. So notice that I have 1 plus tangent squared of theta over 2. So I'm going to replace that with secant of theta over 2 squared. If you are not familiar with secant, cosecant, and cotangent, they are simply 1 over cosine, sine, and tangent in that order. So secant of theta over 2 is equal to 1 over cosine of theta over 2. If you're confused, you can note that this is f sub t squared is equal to f over 2 squared divided by cosine of theta over 2 squared. That's the same thing. But yeah, notice how both sides of my equation are squared, so I can just take a square root, and I note that f sub t is equal to f over 2 times secant of theta over 2, okay? So I have but not just solved my lateral force, I've also solved my total tension force. Now let's just imagine, let's theory craft some numbers and make sure that these numbers make sense because we want to have an intuitive understanding. So for our lateral force f sub x, this is just proportional to tangent of theta over 2. When theta is 0, tangent of 0 winds up being 0. So that means that the horizontal component of the force is 0 when theta is 0. This makes sense because when the carabiners are right next to each other, that means each of them should be supporting half the weight of the climber. When theta starts going out to 180 degrees, that means theta over 2 is 90, and tangent of 90 is actually infinity. And that is where the theoretical infinite force comes from. It is that this horizontal force is blowing up to infinity. So that makes sense. Also note that with the tension, f over 2 times secant of theta over 2, when theta is equal to 0, secant is 1. So that means that the tension will just be f over 2 again. That completely makes sense with our previous understanding. And secant again also blows up to infinity when theta, in this case, is going to be 180 degrees. So So that is everything that's involved. So the interesting thing that comes out of this is that f sub x is the thing that is blowing up to infinity. It is the fact that the carabiners are being pulled together so hard that they will start exerting ridiculous forces on the system. And that is where all the forces are coming from. So I've decided to make a little plot, and instead of us just kind of vaguely talking about some of these numbers, I thought maybe we should go through things. So I've actually written a Python script here, and I have these labels backwards, unfortunately. So what I want to point out, this orange line is the tension force. So this should be orange and this should be blue. This orange line is the tension on the carabiner. And notice, I'm going to zoom in right here. Let's zoom in for 100 degrees. Notice that at theta is 0, you wind up getting half of the total force winds up being the tension, and none of the total force winds up being this horizontal component. But as theta increases, this horizontal component gets bigger. And because it's getting bigger, even though the vertical component's staying the same, this total force, which winds up going as secant, increases as well. So let's zoom out a little. Can I not zoom out? Interesting. There we go. So let's zoom in at something a little wilder. So let's go 180 out to the end of this line, which is 170 degrees. So I've only drawn this to 170. It blows up to infinity as you get to 180. So that's just how I've decided to define it. But notice that once you've reached this outer region, it turns out that the forces horizontally, which are the blue line, winds up matching almost exactly the tension of the carabiner, and is this horizontal force blowing up. And you can see right here, let me zoom in. At 170 degrees exactly, note that this total force is 5.7 times the weight. And notice that this horizontal force winds up being just under 5.7. So that is where all of this comes from. Hopefully this is informative because it educates a little bit on where some of these forces are actually coming out of climbing, and how forces like that come about. Hypothetically, for giggles, first of all, let me fix this. I'm sure you guys didn't come to see Python code. But let me go ahead and see what would happen if I approach 1.7. I'm going to get arbitrarily close to 180. So I'm going to go to 179.9 degrees. And if I run this, notice now that the forces are starting to approach somewhere around 270 times the force of the climber as you approach 180. So this is this exponential, this very steep increase right here. Pretty much everything past 175 starts blowing up so large that the forces involved would be incredibly dangerous. Now, obviously, a lot of this is hypothetical. You do have to be able to exert that for a downward force that could create that and get the carabiners in such a state that they are forced to behave like that. But it is very easy to get your forces high enough that it could actually be problematic for your climber. So yeah, I've kind of taken it just back to this more narrow region here where we can look at it. The reason why I'm going to go back to the talk real quick just so we can talk. So the reason why we should care about this is you want to keep all the forces really low, and understanding how these forces play a matter on weighting your gear matters a lot. It's very easy to think that this is just a normal situation where you're weighting gear in a certain way and you could accidentally exert a very large amount of gear. Again, I'm not a certified guide. I recommend that if you are interested in learning anchor building, you learn how to do it safely and properly. I always recommend going with a guide with people who have not been outdoor climbing before. But again, I hope this was at least informative so you have a better idea of how the forces involved go on. I'm going to link this talk in the description of the video. And I also am going to link a page to the American Alpine Institute's discussion about the American Death Triangle. So the page where I got this image from. And they have their own links, and there's very interesting stuff, so I recommend educating yourself. But yeah, I hope that a deep dive into the math was a little informative about exactly what's going on. But all of this just comes about where the angle being locked in a certain way and the weight pulling down is forcing forcing this horizontal force onto the system that is unwanted and ultimately can be unsafe. So yeah, thank you guys, and I hope that this was informative and you have a good day.